Hi everybody, today we're going to discuss chapter 5. So we look at data compression in general. Okay, so how do we actually do the data compression? So the basic concept is actually by removing redundancies. Now what are redundancies? Okay, if we take examples of image data, so there are three types of image redundancies in image data. The first one is coding redundancies. What is coding redundancies? Okay, for example, in the image, we have only 64 different gray levels or 64 different colors. So we need only actually 6 bits to code them because we know 2 to the power of 6 is 64. But we know typically image actually use 8 bits, okay, which can code up to 256 levels. So in this case, there are some coding redundancies. So I'll show you an example. If we have 64 levels, we need only 6 bits. So from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 all the way to 1, 1, 1, 1, 1, 1. Okay. But if we use 8 bits, then we can see that, okay, the 2 bits in front here is always 0. So that means that we don't really need them actually because they don't really help us to differentiate anything. We can actually remove them. So the 2 bits here is considered the coding redundancies. Okay, the second type of redundancies, we call it spatial or interpixel redundancies. So I have one examples here. You can actually go to the lab manual, lab 6. Okay, so we have this test DCT. We can actually run it. So if you look at these examples here, you can look at the image. So in this part of the sky, you can see that the gray level is very similar. Okay, and then if you look at the part here, the coat and also the hair, they are dark and they are very similar. All right, so actually if you look at most part of the image, okay, if you take any point here, okay, and you compare to the surrounding, so their pixel levels are actually very similar. Okay, right. So that is called interpixel redundancies. Or actually, if we talk about in terms of frequency, then most of the frequency actually are low frequencies, or most of the energy actually focus on low frequency, as you can see here. Okay, so this is the after we transform using discrete cosine transform, a very famous transform used in JPEG. So you can see that actually most of the coefficients, the high frequency, this is the lowest is actually here, the origin. As you go further from the origin, is actually the coefficients for higher frequency, and this is the highest. And you can see actually the bright color actually focus at this corner here, where it's actually associated with the low frequency. And as you move out, you can see it's darker, meaning that the intensity or the magnitude is lower, near to 0. So this is especially true as you go to higher and higher frequency. Their magnitude is even closer to 0. All right, and there is another, and if you look at this, coupled with another redundancy we call psycho-visual redundancy. What is psycho-visual redundancy? So psycho-visual redundancy is, for example, human, we are more sensitive to brightness change than color. I'm going to talk about it later, but I'm talking about this. So we are also more sensitive to low frequency than high frequency. So if you look at this, all right, the image actually consists mostly low frequency. All right, so that this alone actually has helped us to, when we transform to frequency domain, so most energy will focus here, so we can actually ignore, okay, the high frequency because they are very much close to 0, so small that you can actually ignore them. And plus with the fact that we are more sensitive to low frequency than high frequency, so what actually happens when we do compression is we tend to remove all the high frequency. So we'll implement this kind of filtering mask where we keep only the certain part of the low frequency, and the high frequency usually we multiply with 0, or in other words, we are actually removing all the high frequency coefficients. We keep only the coefficients, the coefficients for low frequency. And true enough, if you do the compression by removing the high frequency, okay, In fact, these two images, you don't see much different visually, all right? But actually, when we save that, we save only the low frequency coefficient without the high frequency. And you can see there's not much different. So in other words, the high frequency, basically they are redundant. So you don't really need them. So in compression, usually we remove the high frequency. Okay, right. So I want to show you this fact where we are more sensitive to brightness change than color. So if you look at the lab manual under lab 8, so there is this brightness resolution. So I've created a code. So in this code, you can see that I actually perform compressions. One, I compress the preserve the brightness, so meaning I compress the color. Okay, another one, I preserve the color and I compress the brightness. So if you try to compare, look into more detail, then you will see what I mean by, okay. So if you see the one that preserve brightness, okay, so the resolution is very much preserved, so you can see it's still very sharp as compared to the one that I preserve the color and I compress the brightness, so you can see this is blurrer. All right, so in other words, actually preserving brightness is more important because we are more sensitive to brightness change than color change. Okay, so this is about the three redundancies in image data. Okay, next, so we have two terms here. One we call lossy, another one we call lossless. So lossy is where there's no data, there is data loss in the process of compression. Like for example, in this case, when you try to do compress to the low frequency and high frequency, we actually remove, okay, you can see we remove the low frequency. So we actually, this is a lossy compression, although visually you don't see much difference, but actually there is already some data that has been removed from the original one. So this is called lossy. Lossless is where there is no data loss at all. So whatever that the original data and the one that you compress and you decompress, you get back exactly the same thing. So now I'm going to show you the one that is important in our discussion is the one for called Huffman coding. So Huffman coding is actually a lossless coding where they help us to remove this kind of coding redundancies. Okay, so we're going to look at Huffman code. Okay, so Huffman coding actually works in removing coding redundancies and achieve higher, better coding efficiencies. So understand what is coding efficiency. Consider this case where we try to transmit the local weather conditions to a remote site by using binary code. Suppose in case this first case A here, we have four weather conditions. So we have sunny, rainy, cloudy, and snowy. And then in these particular locations, it appears that the four weather conditions occurs in a very similar probability, equal probability, meaning that in 1 year, chances of having sunny day is 0.25 or quarter. And then the other quarter is rainy day, the other quarter is cloudy, and the other quarter snowy. All right. So suppose we try to design code for it. So we know that there are four conditions. So our intuitive is we just assign 2 bits because 2 to the power of 2 is 4. So we can have 4 unique codes to represent each of the 4 weather conditions. So our code length is 2 bits. So 2. So if you try to calculate the average bit rate, so by multiplying the probability with the code length, so 0.25 multiplied by 2, and we do that for all the weather conditions. So you get average, of course, 2 bits per symbol, or 2 bits per weather condition. Here, the weather condition, we call it a symbol. So we try to code each condition or the symbol. So we find what is the average code length. So it's 2 bits. All right, so this is the coding efficiency that we have for this case A. Now suppose for case B, which is we have slightly different probability distribution. where we have more frequent sunny day. Okay, and then we have second likely happen, rainy, and then we have the least two, cloudy and snowy, only 0.25. All right, so suppose we still use this coding set where we make all of them have equal code length, that is 2 bits each. So again, if you calculate the average bit rate, of course, you get 2 bits. But if you try to code it in a different way, that is, we try to use code set like this, not all having same code length. So we have different code length, like for example, for sunny day, only 1 bit. And then for snowy day, we have the long, and cloudy, we have 3 bits longer. And in this case, if you try to calculate the bit rate, so you take probability 0.5, multiply with the code length 1, and then for rainy, you take probability 0.25, multiply with 2, like here, and so on. And if you calculate, you're going to get a different coding efficiency, which is 1.75, which is less. So we want as less as possible because we're talking about data compression. So we want as fewer bits as possible in average. So obviously, in this case B, with these two different coding scheme, we'll find that this coding scheme with different code length will give us a better efficiency or shorter, fewer number of bits per symbol, 1.75 as compared to 2. So of course, here when I ask which code set is better, then now you see that this code set is better, where you don't use a similar code length for all, but you actually try to code according to their probability. So what is the relationship between the code length and probability? So that is actually the concept, the idea behind Huffman coding. We use less bit to code those very frequent condition or symbol. If you look at here, very frequent, so we use less bit. And the least frequent here, we use longer bit. Okay, so this idea is analogous to minimizing the weight of our bag. So the bag that you carry to classroom, okay, you will try to make it as light as possible. And the bag that you carry back hometown, which you do only once a year or twice a year, okay, then you can have a more heavy bag. But that one that you do frequently, then you want to make it as light as possible. All right. Okay, let's look at the algorithm of Huffman coding. So for Huffman coding, of course, first you need to have the probability, because you need to code according to the probability. And then because we want to always give more codes, longer codes to high probability, so we always sort in. So from smallest to largest, like here, from smallest to largest. And then we will always combine the two by addition. So the smallest two, we combine them. So it becomes 0.3 in this case, and then we sort them again. Okay, we go to step 3. So go to step 2, we order again. So after we combine, we get 0.3. So then we sort them again. So the 0.2 become lower. 0.3, which is the combination of cloudy and snowy, now is ranked in the second. And then 0.5 remain the top. And then we repeat the same step. We combine the two smallest. Now both become 0.5. So then we combine two 0.5 and eventually become 1. And the algorithm stop here. So for each of the combination here, we will assign 0, 1, 0, 1, and 0, 1, all right, for each branch. All right, and then from there, we try to look for the codes. Like for example, how do we get 0 here? That is, just travel from here to here. So you get 0, okay? So next, how do we get 1, 1 here? So you travel 1. So this is this bit 1. And then you travel up. Then you reach here, you get 1. So another 1 here. So 1, 1. So how do we get 1, 0, 0 for cloudy? So you travel from here, 0. This branch, 0. Second branch, another 0. So the middle 0. and then go to third branch, 1. So 1, 1, 0, 0. And then for Snowy, you travel from here, 0. Sorry, 1. So you get 1 here. And then you go up. Then second branch, you meet with 0. So this is the second bit, 0 here. And then to the third branch, you encounter with 1. 1, 0, 1. All right. Okay, let's look at another example. Suppose you have this probability distribution. So again, we're going to sort them. We're going to sort smallest 0.12, and then C 0.13, 0.15, 0.20, and 0.4 the highest. So as usual, we try to combine the last two, 0.25. So we sort again, so 0.25 now rank number 2. And then these two will become 3, number 3 and number 4. And 0.4 remains the top. All right, and then we combine the smallest two and now become 0.35. So now 0.35 rank number 2 above 0.25 rank number 3, and 0.4 remains the top. And then we combine 0.35 and 0.25. So we get 0.6 now rank top, and 0.4 ranks down here. So then when we combine the two, we get the last branch here. So again, to get the code, so A, the code should be, so first branch 1, second branch 1, third branch 0. So 1, 1, 0, 1, 1, 0. And then for C, first branch 0, second branch 1, so 0, 1. All right, and then third branch is 0, so 0, 1, 0. Same goes with D, treble 1, 0, 0. All right, 1, 0, 0. And then here, first branch 0, second branch 0, third branch 0. And last but not least, B, you travel all the way to here, 1. All right, so that is basically about Huffman coding, how you do the coding. All right, so it's very important. It's always come up in your final exam. So we'll look at the sample questions later on. Okay, so that is the encoding part. So how do we decode? So to decode, then you have to read one bit at a time, okay, and then check with the table, because you have no idea what is the length, because it could be 1 bit, could be 2 bit, could be 3 bits. All right, so I'm going to show you how we do the decoding. So we will take 1 bit at a time. Okay, so let's take 1 bit at a time. So I take up the first bit, so 1. So you check table, is there any Huffman code 1? Yes, we have here 1. So B. So we decode 1 as B. So now we empty out the buffer. So now the buffer, we take another bit in, which is 0. So any code 0? No. No code 0. So we take the second bit in. So now we have 0, 0 in our buffer. So any code 0, 0? No. So we take the third one in. So we have 0, 0, 0. Yes, we have 0, 0, 0, which represents symbol E. Okay, done. We clear the buffer, and then we start with this bit. 1. Anyone? Yes, B. Okay, so we clear the buffer again. So now we take out 1 bit from here. 0. No, there's no 0. What about 0, 1? No, there's no 0, 1. So what about 0, 1, 0? Yes, we have C. Okay, so we clear the buffer, and then we take 1 bit in. Okay, 0, no 0. So 0, 0 also no, not on the table. 0, 0, 1, yes. So we have 0, 0, 1, D. So we clear the buffer. Now we take 1 bit in, which is 0, no 0. Now we take 0, 1, no 0, 1. 0, 1, 1, yes, A. So that's how we do the decoding. All right. Okay, so note that the valid code set should not have their prefix. So what is prefix? Prefix means the bits in front. Okay, not entire code, but the first few bits. Okay, example here, if you look at code C110, So this actually has a problem because the prefix 1 here is the same as the code B. So this will create confusion when you have code, when you encounter 1, and you have no idea this 1 represents a code for B or is actually the prefix for C, because both are 1. Okay, so suppose, let's see what problem is going to create if we use this kind of invalid code set. Let's encode BCE using this table. So BCE, B is 1, C is 110, so 1, and then followed by C, 110, and then followed by E, 000. Okay, let's try to decode this and see what is going to come out. Okay, so as usual, we take out 1 bit to the buffer. Any 1 here? Yes, B. So we decode as B. Next, we clear buffer and then we move the next bit in. 1, any 1? Yes, B. So then we clear buffer and then we take another bit in. Any 1? Yes, B. So, and then we take 1 bit in, clear the buffer. So now 0, no code with 0. What about 20? No code with 20. So what about 30? Yes, so E. So now last we have 1 code with 0. And this 0 become undecodable because there is no code with 10. So now you can see that you get entirely different decode a different message. Instead of BCE, now you get BBE. So because of this code table with some bugs. All right, so this is also one of the good way for you to check in your final when you have finished up your Huffman coding. So you have to check whether there's such bug in your code table. All right, so make sure that no prefix like C similar to code for another symbol. Okay. All right. Next, we'll talk about the minimum number of bits to code a symbol. All right. So what is the minimum number of bits to code a symbol according to a very famous Shannon theory? Is negative log base 2 because we're talking about binary system. So base 2, the probability. Okay, so very important so that you know how to do the calculation in your final. So in your final, you're not allowed to bring in any handphone, so you can only use your calculator. So this is how your calculator will look like, scientific calculator. All right, so how do you calculate log 2? Because in your calculator, you have only log 10. All right, if you do not believe me, so let's say it's at negative log 2, 0.5. So negative in bracket 0.5 locked. Okay, so and then closed. So you get negatives. You get negative 0. You get 0.3. So which is not right. By right, log 2 0.5 should be 1. I mean negative. Okay. So so what you can do is if you want to do calculation of log 2, but you have only log 10, so you can always get the results and then divide by log 2. All right. So you get the result as 1. All right. So negative log 0.5 divided by log 2. Okay. So let's try to calculate this. Negative log base 2, 1 over 8. Okay. So let's clear this. Okay. Negative in the bracket. I put another bracket because I want 1 divided by 8. And then I close the bracket. And then this whole thing, I want to lock it. All right. So close the bracket. And then because this is still base 10, so to get log base 2, I divide by log 2. Okay. So you should be getting 3. All right. So this is how you do the calculation using calculator without log base 2. So you always divide by log 2. All right. Okay. So Now, what happens if the symbol has probability 1? So can we try to calculate? What do you get when you do log 1? So 1 log, you will always get 0. All right. So what is the minimum? So you always get 0 bits. All right. So is this consistent with the fact? All right. So actually it is. If a weather condition is always the same, do you bother to send any code? If you know that the weather there is always sunny, then there is no information that you need to transmit because it's always sunny. So there's nothing to transmit, therefore 0 bits. Okay, right. So entropy. So what is entropy? Entropy is the average minimum number of bits. So just now we calculate only the log base 2p, which is the minimum number of bits for one symbol, but in one information system, we have several conditions or several symbols, each with different probability, or same, doesn't matter. So each has their own probability. So you need to calculate their average. So average means you take the probability and then you multiply with their minimum code length. Then you get the average minimum code length. All right, I repeat. So calculate the minimum code length, you use negative log 2p. And then to calculate average, you take this and then you multiply with the probability. So that's why we have the probability multiply with the minimum number of bits. Okay, and then we sum them. So sum them, so you get the average minimum number of bits per symbol. All right. So for example, in this case, if you try to calculate average minimum number of bits entropy, so you take 0.2, multiply with the minimum code length for this symbol, 2.32, and then you add with this one, which is sunny, the probability 0.5, multiply with the minimum code length 1, all right, and so on, and you get 1.76. So this is what we call the entropy. Entropy is what is entropy? Average minimum number of bits per symbol for one information system here. All right. And average number of bits per Huffman code. So if you try to code this using Huffman, so this is the Huffman code. And then we try to compare with the average Huffman code length here. So this is the Huffman code length, 3 bits, 1 bits, 2 bits, and 3 bits. And you take this code length and you multiply with the probability. So 0.2 multiply with 3. So 0.2 multiply with 3 and 0.5 multiply 1, 0.5 multiply with 1. All right. So, and so on. And you get 1.8. All right. So you notice that this entropy is always lower than Huffman code. It will never, the Huffman code can never get lower than that. And if you look at this example, same. Calculate the average minimum number of bits per symbol of entropy. So you take this, their minimum, average minimum number of bits for this symbol, multiply with the probability, and then you get 2.15. All right, and then if you try to compare that with Huffman code, so these are the Huffman code, and these are the Huffman code length, 3 bits, 1 bits, 3 bits, 3 bits, 3 bits. So you take the Huffman code, multiply the code length, multiply with their probability, and you get 2.2. So again, you will find that this Huffman code, it could be close to entropy, and that is what Huffman code designed, so that we can achieve as minimum as possible to this entropy. So if you can achieve to this entropy level, then that is considered the best, the most optimal code length that you can achieve, because you can go very near but never lower than entropy, because entropy is the theoretical minimum, okay, of the code length. All right, so the next question is, why do we bother about entropy? So as mentioned before, no matter how efficient your coding scheme is, you can never go below entropy. All right, so therefore, if you want to improve your coding efficiency, you must find a way to reduce the entropy. So how to reduce entropy now? Because we know entropy very much dependent on the probability distribution. If you look at the first probability distribution like histogram 1, where we have all equal. So if you have all equal, you will find that the minimum is all 2. And then if you try to use Huffman code also, you get all 2. All right, so that is the best that it can go, because entropy is 2, also Huffman can never go below 2. And true enough, if you have look at the Huffman code, it's always 2 bits. So that's the best you can go. But if you have unbalanced probability, like for example, A is more frequent than B and so on, then if you try to calculate the entropy, you get 1.75. And true enough, if you go for Huffman code, so you can practically achieve something like entropy 1.75 as well. So you can see that Huffman code, although it is designed to take advantage of that, but it can never go below the entropy. So so if you want to code something which is to have shorter, so you have to code according so that it can go according to the unbalanced probability distribution. Okay. So in order to change the entropy, so you must change the statistical model of the information. Now, for example, let's say you have this binary image. Okay, so if we try to use one model where you just follow the distribution of the gray level, which is 0 and 1, and in this case, you have only 2, 0 and 1. And if you look at them, their probability also very similar. Okay, the number of pixels for 0 and 1 is almost the same. So, and then if you try to code them with Huffman, so you can only have 0 and 1 because there are only 2 levels. So then that makes no difference. All right, you still have 16 bits here. Now, what should we do? Now, suppose we choose another model. We take advantage of one that you can observe certain trend here. So this, when we say observe certain trend, means there is certain unbalanced probability. Trend means something that occurs very frequent. So we observe trend that is once it is 1, then the next one will also be 1. And then once it is 0, then the continuous will be 0. The following will also be 0. This is what we call the run, all right? So we observe that this image has a very long run, okay? Although it not always happen, but it's very frequent. At least out of 4 rows here, the 3 rows has very long run, except for the second row where after 0, then you have 1. But even then, this run is also considered long. See, a continuous long. All right. So we take advantage of this. So instead of we code using the gray level, which is 0, 1, we code the run length. Okay, we code the run length. So this is different statistic model, not the gray level, but the run length. So suppose we choose to convention always start with 0. So then we represent the image in terms of run length. So the run length was possible will be 0 run or 1 or 2 or 3 or 4, because maximum 4 here, so you can continuous run for 4. Okay. Okay, so we start with the first row. So we always start with the run of 0. So since this one start with 1, so the run of 0 is actually 0. And we know after run of 0 is run of 1. So what is run of 1? Run of 1 is 4 for the first row. Okay, so we are done with the first row. Second row, what is the run of 0? We always start with run of 0, 1. So after run of 0, then it's run of 1. So how many run, continuous run of 1? 3. So again, already 4 pixels, so we are done with second row. And the third row, we start with 0. Run of 0 is 4. So we put 4, and we are done with third row. And the fourth row also, run of 4, 0. So we are done with that. So now we represent the image using the run length. And in fact, you can decode using this. Okay, 0 run of 0, so no 0, and then 4 run of 1, so 4, 1, 1, 1, 1. And then 1 run of 0, so 1, 0, and 3 run of 1, so 1, 1, 1. And then 4 run of 0, 4 run of 0, and then fourth row, 4 run of 0. So you can decode by using this. This is another representations of image in terms of run length. Okay, no more code with gray level, but with run length. Okay, let's see how the distribution, probability distribution of this run length. So we have run length possible from 0 to 4, because this image is of 4 pixels. So maximum up to 4, minimum 0. And if you look at the count in this image, so you have count 0, 1, count 1 is 1, count 2, no count 2 here, count 3 is 1, and count 4, 3. So if you look at the probability here, so the probability is actually higher for long run of 4, and then you can see the probability for short run is actually very low. So then in this case, we have a not balanced probability. So in this case, then we can have a lower entropy. All right. So this is the Huffman code. If you go for it, Huffman code. And total number of bits. So if you see the count 1, so 2 bits for this 0 run length, 1 count of 1 run length, so 3 bits, and then 1 count for 3 run lengths, which we use 3 bits, and then 3 counts for 4 run length. Okay, and the bits is 1, so we need 3 bits. So total only 11 bits as compared to original 16 bits. So this is how we actually take advantage of the long run length. And this run length is called, there's a name for it, it's called run length coding, which is very efficient for a black and white document, and has been used in coding document like this in fax. Of course, now we don't use fax anymore, but still when we code a black and white document like this, we'll find this to be useful. If you look at this document here, you can see the run of white, the background, the one is very long. And then the run for black, which is the character, is very short. So they have very clear difference in terms of the run length for the background and also the words. So we can take advantage of that because we know there is a trend. The trend, what is the trend? A long run of one white and a short run of black. So that will give you a very unbalanced distribution and therefore low entropy. And if you try to do Huffman coding with that, then you will get a very efficient representation. All right. So now we're going to look at the past year questions. I'm going to sample. See how much time do I have. Okay. I have 46, 48, 50. All right, so this is how the question looks like. So you are required to differentiate between lossless and lossy. So lossless, basically no information loss. And then lossy means there is some information lost. Okay. And then coding redundancies. So 2 types. So you can talk about coding redundancies and interpixel redundancies. So you have to give example. So coding redundancy meaning example 8 bits of pixel, that 8 bits per pixel can code up to 256, but if you use it for 16 grade levels, which needs only 4 bits, then it's a coding redundancy. Interpixel means the adjacent means the neighboring pixel tends to be highly correlated. So their values tends to be similar to each other. So you don't need to repeat the value. So you can actually code one and then the rest you can just take their difference, and the difference tend to be small, which you can use less bits to code them. Okay, entropy. So what is entropy? Entropy is actually the minimum average. Okay, not really how many, but the minimum average minimum number of bits per symbol. Okay, it's actually available in the notes. Entropy, average minimum number of bits per symbol. All right, so this is the right answer. Okay, so we will be given image usually. So you have to calculate the entropy. So so you have to come up with their histogram. So you're going to calculate for each gray level how many pixels are there. So in this case, 200, there are 8 of them, and so on. So you can divide by the total, then you get their probability. And then you calculate log 2, as what I have shown you. And then you multiply the probability with the minimum number of bits. And this is what you get, and then you sum them. So 1.75 is the entropy. So next, you need to generate the Huffman code. So to generate Huffman code, then as usual, you have to always sort. And then you always combine the lowest two. All right. And then you sort again, and then you combine. And then the bits is by traveling from here up. So 1, 1, 1, this one, 0, 1, 1. So 0, 1, 1. This one, 0, 1, 0, 1, and this is 0. So this is the code set. And all right. Next, Huffman code 2. So you are given image like this. So you have to compress it. So you need to describe the type of redundancy in the image. So the first one is actually coding redundancies because you're using 8 bits. But here you have actually, how many levels are there? You have only 5 different levels, 80, 100, 120, and so on. So actually for 5 gray levels, you need only 3 bits to code them. So 8 bits is actually redundant. Another one is interpixel redundancies, and if you look at it, okay, the neighboring pixels tend to be similar. All right, so you can actually try to look at their histogram. So 0 difference between the 2 adjacent pixels. Okay, there are 8 of them. So you can see this one and this one, difference 50, this one and this one, different 0. Okay, this one and this one, different 150. This one and this one, different 0. So 1 different 0, 2 different 0, 3, 4, 5, 6, 7, 8. So 8, 0 difference. And then 20, you can see 20, how many difference of 20? 1, 2, 3, 4, 5, and then 6. All right, 7 actually. All right. And then 30 and 50. So you can see that actually in this statistic, the small difference tend to be more frequent than the high difference. So that, in other words, indicate interpixel redundancy. So neighboring pixels tend to be similar. Similar means small difference. Next, you calculate their entropy. Okay, so the entropy, like what we have seen previously, so you come up with their histogram. So you calculate the probability. Take this, divide by the total. So the total is 20, 19, 25. So 6 divided by 25, you should get 0.24 and so on. So again, you take their probability, multiply with the log base 2 of the probability, and then sum them. Don't forget to negate. So you should get a positive number. So this is actually the average minimum number of bits per symbol. All right. So calculate what is this number representing. Is actually average minimum number of bits per symbol. Again, you have to perform Huffman coding. So then just do the Huffman coding like what we have done, as in the notes. So actually note that their Huffman code can actually, because the branch can be, you can always 0, 1, 0, 1, 0, 1, or you can have 1, 0, 1, 0, 1, 0. So their code can actually be the reverse of each other. All right, the third one, what is lossy lossless? We have actually discussed that. one with no data loss, one with data loss. And what is entropy? So again, the minimum average number of bits per pixel. And then generate Huffman codes is pretty much like the previous question. So you need to come up with the probability, and then you will do the Huffman coding. Okay, you have to sort them, and then combine the smallest two, and then sort again, and so on. All right. So then, so this is the one that is slightly different. Evaluate the performance. Okay. So evaluate performance. How do you evaluate? So you calculate the entropy. Okay. So entropy, and then you calculate the average bit rate. So what is the average bit rate? That is, you take the Huffman code, you multiply with the probability. So that is the average. Okay, so you can see the Huffman code is always higher than entropy. And last but not least, to calculate compression ratio. So the uncompressed file size. So uncompressed file size, you can look at here. There are 25 pixels, and we are talking of 4 bits per pixel. So 25 times 4. So 100 bits. And size after compression, of course, then you will take your Huffman code, and then you calculate. So for each symbol, okay, what is the Huffman code length? And then you try to add them together, so you should get like 43 bits. So then you take compression ratio 100 divided by 43, you get 2.3255. All right, so that is all about chapter 5. Thank you.